In this video, we're going to talk about how to make a crystal oscillator circuit using the Colpits oscillator circuit. Now, for those of you who remember the Colpits oscillator circuit, all you need to do is replace the inductor with a crystal oscillator. And then you could turn it into a crystal oscillator circuit. So this is the electrical symbol of a crystal oscillator. The one I'm using is a ceramic 455 kilohertz oscillator. Now this is going to be attached to the base of a transistor. And I'm using an NPN transistor in this example. Now at the emitter of this transistor, I'm going to have an emitter resistor and a bypass capacitor crosstalk. The purpose of the bypass capacitor is to increase the gain of the amplifier circuit. So let's call this RE, the emitter resistor, and then CB, the bypass capacitor. And then the emitter resistor is going to be connected to ground. Now between the base of the transistor and ground, we're going to have a capacitor. And let's call this capacitor C2. And then we're going to have the base resistor, RB, and I'm not going to connect that to VCC. Instead, the base resistor is going to be connected to the collector of the transistor and RC as well. Now RC is going to be connected to VCC, the collector supply voltage. And then we're going to have another bypass capacitor which goes to the output. Now I'm going to have another capacitor connected on the other side of the ceramic oscillator, and this is going to be C1. Now C1 is also going to be connected to the collector of the transistor. So keep in mind, this is the base of the transistor, this is the collector, and this is the emitter. Now the specific transistor that I've used in this circuit when I tested it, it was the 2N4401 NPN transistor, for those of you who might be interested in. Now the values of the bypass capacitor, for both of them I made it 220 microfarads. And I want to make sure that the reactance generated by these two bypass capacitors are relatively low at the operating frequency. And keep in mind, the capacitive reactance is 1 over 2 pi Fc. So as the frequency of the circuit increases, the capacitive reactance decreases. So I want to make sure that those two capacitors do not provide any significant impedance to the AC signal at its operating frequency. Now let's talk about the values of RC, RB, and RE. So when I tested this circuit, I chose a value of 33 ohms for RE, and for RC, I chose a value of 330 ohms. Now the voltage gain of the circuit is going to be RC, assuming that the load resistance is infinity, divided by the AC emitter resistance plus RE. Now if the current of the circuit is low, typically this is a low value, and so the voltage gain is going to be approximately RC over RE. So I wanted RC to be relatively high to RE. But if RC is too high, the circuit will fail to oscillate. In the experiment that I tried, an RC value of 510 caused the circuit to no longer oscillate. Using the 470 ohm resistor, it still oscillated, but at 510 it discontinued oscillations. For RB, I use a 100 kilo ohm resistor. If RB is too high, it will also fail to oscillate. Using the value of, let's say, 220 would be too much for it. Now for C1 and C2, during one Pacific trial, I use a 1.7 nanofarad capacitor for C1 and a 240 picofarad capacitor for C2. And then the output frequency measured was 454.5 kilohertz. Now C1 and C2 do affect the operating frequency of the circuit, but not by much. For the most part, the frequency is close to 450 kilohertz. It can vary a bit, but it's very close to the oscillator, the ceramic oscillator frequency. And the second thing is, these circuits are very stable. Whenever you use a crystal oscillator circuit, the output frequency doesn't change much. It's very, very stable, which is one of the main advantages of using a crystal oscillator circuit as opposed to a regular oscillator circuit. It generates a reliable, stable output frequency. Now for this particular circuit, I didn't get a perfect sine wave. The waveform looks something like this. So notice that the width of the peak of the wave is higher, or longer rather, than the bottom part of the wave. This is shorter. So that's the type of output I got for this particular circuit with the values presented here. Now let's make a table with some of the values that I've used with this circuit. So we're going to have C1, C2, and this is going to be the peak output voltage, not the RMS voltage, and then the frequency. So using a capacitance of 0.105 microfarads, or equivalently 105 nanofarads, and for C2 it was a 4.7 nanofarad capacitor, but when I measured it, it measured out to be 4.56 nanofarads. The output was 80 millivolts, and the frequency was 436.5 kilohertz. But nevertheless, the waveform was a nice, smooth sine wave. Now, changing the values of C1 and C2 doesn't really significantly impact the output frequency. For example, cutting C1 in half while keeping C2 the same. The output voltage was about the same, but the frequency didn't change much. It was 436.1 kilohertz. So as you can see, the frequency is relatively stable to small changes in the capacitance values. Now making C1 9.68 nanofarads and changing C2 to 314 picofarads. The output voltage was higher, it's 1 volt, and I got a higher frequency of 444.8 kilohertz. At this point, it wasn't a perfect sine wave. The peak of the wave was a little bit wider than the bottom part of the wave. But you can see the frequency change a little bit, but not too much. And then using a 4.56 nanofarad capacitor with a 103.6 picofarad capacitor for C2, the output voltage was 600 millivolts, a little bit less, but an output frequency of 451.8 kilohertz. And then this is the one that I put in a circuit prior to this where I got a frequency of 454.5 kilohertz. And so as you could see, changing the values of C1 and C2 doesn't really impact the frequency too much. It does affect it, but not by that much for the most part. And so the output frequency tends to be the resonance frequency of the ceramic oscillator. Now, using these values, I replace the ceramic oscillator with a crystal oscillator, one that is set to operate at 4 megahertz. And for the most part, I got a distorted wave. It wasn't a nice sine wave, but the output frequency was 3.999 megahertz. And so whether you use a crystal oscillator or a ceramic oscillator, this circuit will work for both of it. But you may need to adjust C1, C2, and some of the resistance values when testing it out. So that's the basic Colpits crystal oscillator circuit. So now you know how to design it, and you also know how to test it. Now let's talk about the crystal oscillator. So this symbol indicates that you have a quartz crystal, or it could be a ceramic crystal. But let's say it's a quartz crystal, which is made up of silicon dioxide attached to 2 metal electrodes. Now, whenever you apply a voltage to a quartz crystal, it will vibrate. It will generate a mechanical force. And conversely, if you apply a mechanical force to a quartz crystal, it can generate electricity, known as piezoelectricity. I've actually have another video on that, which I'm going to put in the description section below. So for those of you who want to check that out, feel free to take a look at the links there. But this is the symbol for a piezoelectric crystal. Now, the equivalent circuit model is as follows. You have a capacitor in series with an inductor in series with a resistor. And these 3 components is parallel to another capacitor. So we're going to call this R, L, and then CS and CP. So CS represents the capacitance of the crystal, whereas CP represents the parallel capacitance of the plates. Because whenever you have 2 metals separated by an insulator, basically it works as a capacitor. So that is the equivalent circuit model of the crystal oscillator. Now there's 2 frequencies that you need to be familiar with. Fs, the series resonant frequency, and Fp, the parallel resonance frequency. This frequency, the series resonant frequency is used more often. And for the ceramic crystal oscillator that we used in this experiment, that was set to 455 kilohertz. Now for this graph, we're going to have XL, the inductive reactance, on the positive y-axis, and XC, the capacitive reactance, on the negative y-axis, and frequency on the x-axis. So this is Fs, the series resonant frequency, Fp, the parallel resonant frequency. To the left of the series resonant frequency, or below it, the circuit is mostly capacitive, and then it's inductive above Fs. Below Fp is once again capacitive. So that graph shows you the relationship between the reactance of the circuit and its frequency. So at the series resonant frequency, notice that the impedance is 0. XL and XC, they're both about 0 in that circuit. So that's the impedance C will be 0 as well. Now at the parallel resonant frequency, Fp, the inductive reactance and the capacitive reactance are very, very high. XL is high, XC is high. The impedance is still about 0 because these two will cancel each other out. So at both Fs and Fp, Z, the impedance, is set to 0. But at Fs and Fp, XL and XC, they're very low. They're close to 0. Whereas at Fp, the parallel resonant frequency, XL and XC, they approach infinity. They're very, very high. That's given the crystal oscillator circuit a high quality factor. So that's the basics of the Colpits crystal oscillator circuit. So now you know how to design it, and thanks again for watching this video.